In the last class we started bandpass signal representation, and in this class we will also continue the same topic, and we will start bandpass signal and more or less bandpass system representation in this class. So, in the last class what we have seen is that a bandpass signal can be represented as a low pass signal with some after doing some operation. So, what we have seen is that if we have a bandpass signal with this kind of spectrum, any spectrum, this is Fc, then we can first suppress the negative side by multiplying by 2 times u of f, that is the unit step function, and then we will get again a bandpass one sided spectrum. The resulting signal will have this spectrum, negative side will have nothing. Then we can shift this spectrum here, then we will get a signal with this kind of spectrum. So, this will be a low pass signal, and this is called the low pass equivalent signal of this bandpass signal. So, we have seen the relationship between this signal and this signal, and in particular we have seen how to construct the bandpass signal from the low pass equivalent signal and how to construct the low pass equivalent signal from the bandpass signal. The bandpass signal is a real signal, but the low pass equivalent signal will be complex signal, because there may not be any equivalence, it may not be any symmetry in one side of the bandpass signal. Whatever is there in the positive side will be also there in the negative side, with some phase will be negative, but magnitude will be same. But in one side itself there may not be any symmetry. So, when we take only that part and bring it to 0 center, then we may not have any symmetry. So, the resulting low pass equivalent signal may be complex. In general it is complex. Okay. So, we have also seen how to construct this signal, what is the real part and imaginary part in terms of this signal, how to construct this signal. And we have also seen that for a communication system, though we will be transmitting the bandpass signal through the channel, ultimately the whole system in the transmitter as well as the receiver may not be designed for the for that particular band which is lying in the in very high frequency. So, what we can do is that we can design the signal as a low pass equivalent signal. We can design the low pass equivalent signal first, because that is the baseband signal, that is a low pass signal with some bandwidth. So, designing that signal is easier, because processing required to design that signal, to generate that signal is easier, with it requires low cost electronics, and then we can do up conversion to get the bandpass signal for that and then transmit that. At the receiver, on the other hand, we can first receive the bandpass signal, then do down conversion to take the low pass equivalent signal, and then do required processing to detect the message. So, the main significant processing at the transmitter as well as the receiver may be done in low pass, on the low pass signal, in the low frequency. So, with that in mind, we saw that we can represent a communication system this way. This is the diagram. Message in the transmitter, first this low pass equivalent signal of the transmitted signal is designed. So, this is design of some low pass signal. So, this is quite easy, and then we do up conversion to get the bandpass signal from the low pass equivalent signal, and then transmit it through the channel. The receiver first does down conversion on the received signal to get the low pass equivalent signal, and then does all the processing on this low pass equivalent signal to detect the message. So, if we represent this whole block, channel including up conversion and down conversion in the transmitter and receiver respectively, we can consider this as a single channel, and then this equivalent channel takes a low pass signal as input and gives a low pass signal as output. So, this channel is now a low pass channel, and it is we can we can consider from now on that the channel is always low pass, but the channel is now complex, because the low pass signal is complex, low pass signal, that is input transmitted, is complex, and the output is also complex. So the channel is complex baseband channel. So we said that from now on we will consider such a channel and consider the task of detection of message from the received low pass equivalent signal and how to design the low pass equivalent signal also. But there is one thing we have not yet done, that is we have said that this is the equivalent low pass channel. Now if this channel is given, say this channel has impulse response HT, which is bandpass, then how to get the equivalent low pass channel? We are given the bandpass spectrum frequency response of the channel, which is bandpass. Now from there we are going to actually consider the low pass equivalent channel. What is the impulse response of that low pass equivalent channel then? So we are going to investigate about that in this class. So before doing that, we will consider also another topic and another small question about the bandpass signals itself, and that is, how does a bandpass signal really look? If you plot a bandpass signal, how does it look? We have seen that you can represent it as a low pass equivalent signal, but in practice, how does the bandpass signal itself look? So we are going to first see that. So usually the bandpass signal will look like something like this. It will have some envelope, say something like this, and of course the negative side also will be there. Then so this is how usually a bandpass signal will look. So this sinusoid, which is inside this envelope, is has about the frequency is about Fc, and if we now this envelope, this waveform, this is called the envelope of the signal. Now suppose we have SLT. We know that the bandpass signal ST can be represented as represented in terms of a low pass equivalent signal, that is SLT. Then we can write SLT is a complex signal, so we can write it as something, some magnitude times e to the power j theta t. Theta t is the phase and at is the magnitude. So now if we write that way, then we have this representation of the low pass equivalent signal. Now what is AT here? AT is the magnitude, x square t plus y square t. If you remember from the last class, xt is the real part of SLT and yt is the complex imaginary part of SLT. So the magnitude of SLT is root over x square t plus y square t, and theta t is the phase of SLT, so it is tan inverse yt by xt. Now once we have that, what is ST? ST is the real part of SLT e to the power j 2 pi fct. This we have seen in the last class, that the bandpass signal can be expressed in terms of the low pass equivalent signal this way, and that is real part of, take this representation of SLT and put it here. So, we will have a t times e to the power j common, then 2 pi f c t plus theta of t. Now, what is the real part of this? This is a real quantity, real number, a real function. So, what is the real part of this? Cos of this. So, the real part of the whole thing is a t cos 2 pi f c t plus theta t. Now, here is the envelope, a t is the envelope, and this is the phase. Now, you can see that this signal, if you plot, this will really have this kind of shape. Cos omega c t, 2 pi f c is the angular frequency omega c. So, omega c t plus theta t. Cos omega c t is the kind of the carrier signal, that is this sinusoidal, and then it will have theta t phase shift. It will have some phase shift which will change with time, and then AT is a low pass signal. As you can see, it is a real low pass signal, because it is the real part, it is the magnitude of a low pass signal. So, it will be positive real signal. So, it will be this kind of signal. So, this will be really the envelope of this whole signal, because this is a very high frequency signal which is varying very fast, and then you have the AT times that will actually change the magnitude slowly. AT is a low pass signal. So, it will have some slow variation compared to the high frequency carrier signal. So, it will vary the magnitude of the sinusoidal signal. So, it will act as an envelope for the carrier signal. So, here this is the envelope AT. This is the envelope AT, and phase theta t is actually, it will change here. So, we have seen what is envelope and phase of a bandpass signal, and envelope and phase, envelope specially has a very pictorial representation. Envelope is basically actually the envelope of this signal. As you can see, this signal is the envelope. Now, we have so far seen two things. One is, we have seen two representations of a bandpass signal. One is as a low pass equivalent signal. So, it will be complex low pass signal which will represent the bandpass signal in a way. So, we can get the bandpass signal from the low pass equivalent signal, and low pass equivalent signal from the bandpass signal. And we have also seen that another representation where ST is represented in terms of an envelope and a phase with some carrier frequency. So, here you get an idea of how the signal will look like. So, it will basically have that AT envelope. But we need to also ask, when we do these conversions from the complex, from the bandpass signal to low pass equivalent complex signal, how does the energy change? What is the relationship between the energy of the baseband low pass equivalent signal and the real bandpass signal? When you do this conversion, what happens to the energy? So, that we will now see. So, let us, so this is, we are going to find out the energy of a bandpass signal in terms of the low pass equivalent signal. So, the energy is defined this way. This is Now we know that the bandpass equivalent signal is this in terms of the low pass equivalent signal. If the low pass equivalent signal is SLT, then the bandpass signal is real part of SLT e to the power j 2 pi FCT. Now Now, how have we got this? This is basically here you can see that from the previous page we have this. So, real part of SLT e to the power j 2 pi FCT, that is real part, so that is the ST. So, we have here real part of this is basically this part, this thing, and this is actually expressed in terms of envelope and phase here. Now, if you take the square of that which is required, so here this will be square. If you take the square of this, what we have is cos square this. Now, what is cos square theta? What is, we can express cos square theta as half 1 plus cos 2 theta. So, using that, now we have this term, square of this is a square t. So, square s square t is a square t, half of 1 plus cos 2 times this, that is 4 pi FCT plus theta 2 theta t. So, now if we take integrate separately these two parts as we need here. So, this inside quantity is basically this quantity is this. Now, we need to integrate these two parts, half a square t and half a square t times cos of this. So, once we do that, we actually have this. If you integrate half a square t is nothing but SLT square, because AT is the magnitude of SLT. So, we have this part and then half inside SLT square, this is magnitude square, times cos of 4 pi FCT, that is 2 times this angle, this plus 2 times theta t dt. So, once we have this can be written approximately as half only the first part. Why? Because what is this signal? What are we integrating in the second integration? What we are integrating there is that if you see try to draw the waveform of this inside function, it will also be a bandpass signal, because this is a carrier signal with some 2 times theta t, the frequency is 2 fc and the phase is 2 theta t, and the envelope is SLT mod SLT square. So, it will look like SLT mod SLT square is the envelope, and then this is the signal. So this is a very high frequency, 2 times Fc is usually a very high frequency, and this is a baseband real signal. So this is the envelope, and we are integrating this signal. Now when we are integrating this signal, you can see that since 2 times Fc is very high, there are many, this oscillation is very high frequency. So if you now take one cycle at a time, what is the integration? One cycle at a time. If you take only one cycle, because this oscillation is very high frequency, what you can expect is that in the one period of this oscillation, this envelope is not changing much, because this is a low frequency baseband signal. Mod SLT square is a baseband signal, it is a low pass signal. So if you magnify and draw only this one period here, you will find it is a signal of this type, where the magnitude is not, this is same as this. So here the magnitude is not varying much, the envelope is almost fixed here, because this is a very small part of this envelope, and envelope is a low pass signal. So this integration of this signal in this interval will be 0, because it is a sinusoid of period 1, one period integration of a sinusoid. So now if you continue doing that, in this small interval it is 0, integration is 0, similarly in this small interval it is 0, this way you keep doing it, the whole signal will give you almost 0. It is almost because the envelope is not really constant here, it is changing very slightly. So this integration will not be exactly 0, but almost 0, the error will be negligible. So we can say that this integration is only this part, because this part will give you almost 0. So this is almost half times energy of SLT. So what we have seen is that the energy of the band pass signal is almost same as the energy of the low pass equivalent signal, half of that. So this is something interesting, because now we know that we can, if we treat the low pass equivalent signal, if we know its energy and then we know that the band pass signal's energy is proportional to that. So we can keep that in mind, and this will simplify a lot of our analysis. So we can treat now the low pass equivalent signal and assume the band pass equivalent signal to have the energy half times the energy of the low pass equivalent signal. Okay. Now we will go into the representation of linear band pass system. So in the last class we saw that this is an equivalent diagram of a communication system, where this whole thing is treated as a channel, and this is now a low pass complex channel. But if we are given the impulse response of this channel is then what is the impulse response of this channel? Now we will see that relation now. So to do that development, we need to represent a band pass system also, just like we represented band pass signal in terms of low pass system. So suppose the impulse response of the band pass system is Ht, and it has frequency response Hf. Then we know several things. One is that Ht is real and Ht is band pass. Now Ht is real, that means that H of f is H star of minus f. This is a conjugate symmetry. The magnitude is same at f and minus f, and phase at f is negative of phase at minus f. So this is the conjugate symmetry. That is, the value at f is the conjugate of the value at minus f. Okay. Now just like we did for the for the bandpass signals, let us say this is suppose this is HF, and we are drawing only the magnitude. Then just like we did for the bandpass signals, we say that H plus F is, take only the positive side. So basically HF if F is greater than 0 and 0 if F less than 0. So this you can also write as UF times HF. Now here for bandpass signals we actually had 2 times this here, but here we are not doing that for some reason, later we will see later. Okay. Now again similarly this is missing a scaling, so which we will neglect for time being, and later we will explain why we have done this. And again just like bandpass signals, we will shift this, so this is basically only one side, H plus F. Now HL of F is H plus F plus Fc. So you basically shift it here. So this spectrum is now this Fc is brought to 0. Now in terms of HLF, now we can write HL of, so what is HL of F minus Fc? It is basically H plus of F. So H plus of F can be, so we can write this, H of F for F greater than 0 and 0 for F less than 0. So we can write that H of F, so H of F is HL F minus Fc. So HL F minus Fc is basically H plus F, that is this. So if you add this with the negative part of it, which we have removed, so that part we can get by taking HL star minus F minus Fc. So what did we have here? HF, we want to get this signal from this. This is HL of F minus Fc. So how to get this signal? First keep this signal and then add this part. Now how do we get this part from this signal? It's basically first invert it. How do you do that? Take this positive side into negative side and negative side into positive side. We simply take the minus of that function. So HL, replace F by minus F. So that is HL of minus F minus Fc. But this is not really the negative flipped version of this signal. This has the phase negative of this. So you have to take conjugate of this. The magnitude we want same, but the phase we want negative. So we need to have HL star of that function, flipped function. The flipped function is HL minus F minus Fc. Then we need to take the conjugate of that. So that is HL star of minus F minus Fc. So once we add these two, we get this function. This part is basically the positive part, this part is the negative part. Okay. So from here we can also write that Ht is HL t e to the power j 2 pi Fct plus HL star t e to the power minus j 2 pi Fct. These are basically the inverse Fourier transforms of these two. So HLT is the inverse Fourier transform of HFT, H capital H L of F. So then we can use the well known properties of Fourier transforms to see that really the Fourier transform of this, inverse Fourier transform of this is this. Similarly here. Now this can also be written as real 2 times real part of HL t e to the power j 2 pi Fct. Okay. Now this is because this part is the conjugate of this part. So we can take only the real parts will remain, imaginary parts will actually cancel. So this is what we have. The actual impulse response is expressed in terms of the low pass equivalent of the impulse response. This is what we also did in the case of representation of band pass signals, and we have done the same thing again for band pass systems. Now we will see the relationship. Why have we done these two things? We have represented band pass signals in terms of low pass equivalent signals, low pass equivalent signal of the same signal. Then we have represented band pass system in terms of low pass equivalent of that system. Now, so we knew that we have a band pass signal, we can give that as input to the band pass system, and then we will get some output. That is also a band pass signal. Then we have a low pass equivalent system of that, low pass equivalent signal of this signal. Then if we give this as input to this signal, what do we get as output? Would we really get the output as a low pass equivalent signal of this output? That is what we want to see. And this is a very interesting idea, we will use that also later. So what we are saying is that we have a bandpass signal ST, a bandpass system HT. We give this as input to this and we get some output, say RT, we receive this. From here we have low pass equivalent of this signal is SLT, and we have also seen how to get low pass equivalent system of this system, that is HLT. It is very similar to this we have seen just now. Now we give this input, what would we get as this output? That is the question. Shortly we will see that we will actually get the output which is the low pass equivalent of this output. So that is something very interesting. So this is also low pass equivalent. Okay. Now let us see that. So this we are seeing response of a bandpass system to bandpass signal, response of this bandpass system to bandpass signal. We want to express this whole operation in terms of low pass signals and low pass systems. That is what we want to see. So RT is the output for ST input. So RT, now we express in terms of the low pass equivalent signal. Now we have not yet seen that the output of this system is actually the low pass equivalent signal. We do not yet know this. We are trying to see that this is true. So we know that RT is the real part of RLT e to the power j 2 pi fct. Similarly, ST is real part of SLT e to the power j 2 pi fct, and again HT is 2 times real part of, remember there was a difference of scalar in the representation of bandpass systems. Okay. So now we can also write these things in terms of in the frequency domain. What do we have? In the frequency domain, R of f, that is the spectrum of this received signal, is S of f times H of f. That is the spectrum of the frequency response of this system times the spectrum of this input signal. Now this can be written as half. What is the expression of SF in terms of the low pass equivalent signal of SF? So SF in terms of SL of f, SF in terms of SLF. We have seen just now for systems. It will be same thing for signals also, we have seen in the last class, but it will have only a difference of scalar. Just now what did you see for systems? We saw that HF in terms of HLF is this. Similarly, for signals also we will have the same thing, but there will be half here. So we have half SL f minus FC plus SL star minus F minus FC times HF. HF, just now we saw that HF is HL F minus FC plus HL star minus F minus FC. Okay. So, this is, we have just replaced SF in terms of SLF and HF in terms of HLF. Okay. Now, remember that SL of t and HL of t, the inverse Fourier transforms of SLF and HLF, are narrow band signals. Narrow band signals. So, we can say that SL of F minus FC is 0 for F less than 0. Why? Because SLF is narrow band, it is low pass narrow band signal. So, its frequency response, its Fourier transform is like this, it lies here, something like say this SLF. So, what is SLF minus FC? It is the shift here. So, SLF minus FC, this is SLF and this is SLF minus FC, this will be something like this. So, this is 0 on the negative side. So, this is what it is. Similarly, HLF minus FC is 0 for F less than 0. Now, let us multiply these terms. This is 0 and this is 0 for the negative side. So, this is 0 on the negative side, and what about SL star of minus F minus FC? It is the flipped version of this and then conjugate. So, flipped version of this will have positive side 0. So, if you take this product, this is at less than 0, this is 0, this is 0 at F greater than 0. So, the product will have 0 everywhere. We have one function which is 0 at negative side, it has something like this spectrum, and this part has positive side 0. So, let us say it is like this, then the product of these two will be 0, because this is 0 at negative side, this is 0 at positive side, everywhere the product will be 0. So, only product, so similarly this times this also will be 0. So, only product which will be non-zero is this times this. So, we can say that RF, so RF is this half and these two also, because this both of them are have some positive side components. So, these two times these two, these cross terms will be zeros. Plus SL star minus F minus FC times HL star minus F minus FC. Now, this is RF, now what is this RLF? You can see that this is RL of F we have replaced this as RL of f is SL of f times HL of f. That means it is the product of these two frequency responses. That means RL of f is the spectrum of the output signal here. So that is, so RL f is the output spectrum of this, and then RF is the output spectrum of this input and this system. So, and we have got a relationship between them, the output spectrum here and output spectrum here, and that relation is that RF is this in terms of RLF. So, this spectrum in terms of this spectrum is expressed here. Output spectrum here is expressed in terms of the output spectrum here. So, but what is this really? This thing which is the output of the bandpass system RF. This is nothing but the up converted version of the RL signal. So, here we can see that this RLF is really the low pass equivalent of RF, because it is expressed this way. So, RF is really, RL is really the low pass equivalent signal spectrum of the RF. So, we have showed that this RL, this output will really be RL, the low pass equivalent signal. So, how did we show it? Let us summarize. We have seen, not this, we have seen that this output is RT expressed in terms of the low pass equivalent. We do not know whether the output of this is really RLT, we are going to verify that. So, we have represented RT in terms of RLT, HT in terms of HLT, ST in terms of SLT, then computed the spectrum of this as product of these two spectrums, then taken their low pass, represented those two spectrums as in terms of their low pass equivalent spectrums this way, and taken these two products, and these two products, the product of the low pass, these two things we have got as this, and then we have assumed that this low pass equivalent spectrum of this and low pass equivalent spectrum of this SLT and spectrum of HLT, the product of them we have assumed to be RL of T, RL of SLF and HLF, the product is RLF. Then we have seen here that this RF, which is the output of the bandpass system, is really expressed in terms of the product of SLF and HLF this way. And from this representation we see that RLF, which is the product of these two, is really the low pass equivalent of RF. So, RLF, which is the product of these two, means which is the spectrum here, output spectrum, is really the low pass equivalent of this spectrum. So, that means the output of this is really the low pass equivalent of this output. So, we have verified that if we have this bandpass system and if we represent the signals and the systems in terms of their low pass equivalent signals and systems, then we really have this output of the low pass equivalent system. When it is excited by the low pass equivalent signal of this input, then the output will also be the low pass equivalent of this output. This is what we have verified. So, now we can treat a bandpass system without any loss. We can treat a bandpass system in terms of bandpass low pass system, because whenever there is a bandpass system, it is difficult to suppose implement such a system. We want to implement a bandpass system with some transfer function, then we can take the corresponding low pass equivalent system and design that. Then suppose we want to give a bandpass signal as input to the bandpass system. We have a bandpass system, we want to implement that, and then we want to give a bandpass signal as input, and then we want to find out the bandpass output. Then we can do that whole thing in terms of a low pass system and low pass signal, exactly like we had drawn here. So we want to implement ht and we want to find out this output. So what we can do is take the low pass equivalent signal. If it is difficult to implement this system, then it is not possible to do this way. Then we can take this. So to do this down conversion, do this down conversion also, and implement its low pass equivalent system and find out the output. This then do up conversion. So we will get RLT here and then we can find out RT by doing up conversion. So this is basically down conversion. This is the low pass equivalent system. So instead of implementing this system, we can do this way, because this will be cheaper, because this is a low pass system. Okay. So we have seen in this class that what we had seen in the last class, we have actually defined that now. We had seen in the last class that we can represent this up conversion channel and down conversion as a single channel, as low pass channel. Now we know now that there is a relationship between this channel and this channel. If this channel has impulse response ht, this channel has the impulse response hl of t, which is the low pass equivalent of this impulse response. So this is something interesting. So this is what we have seen. Now there's all these things you can study from the book by Prokis. I am also teaching from this book, Digital Communication by Prokis. And at this point, after these two classes, you should be able to also solve this exercise exercise 1 from Prokis, fourth chapter of this book, exercise number 1, that is the exercise 4.1 from this book, Prokis. It is basically an exercise on Hilbert transform. It has these components. Please try this exercise at home, and I will solve some particular parts of this exercise in the next class. So it also asks, it actually asks to prove some relationship on Hilbert transform. So for example, part A is if xt is same as x of minus t, that means it is symmetric signal, even, also called even. That means the positive side is exactly the mirror image of the negative side. So for example, it's like this, then it is like this. Then the Hilbert transform x hat t is minus x hat minus t. B is similar if xt is minus x of minus t, then x hat t is x hat minus t. So this can be just use the for proving these two, just use the definition of Hilbert transform, the convolution of xt with 1 by pi t, that is the Hilbert transform of xt. Use the definition, and simple substitution of variable will lead you to this to the solution of these problems. And then there C, for example, is if xt is cos omega naught t, then x hat t is sin omega naught t. So for solving this problem, you can use this and then do this solve this problem in frequency domain. So you know the spectrum of Hilbert transformer HF. Multiply with this, so this has XF as half delta omega. So if omega minus omega naught plus delta omega plus omega naught, then multiply by HF and take the inverse Fourier transform. You will easily get this. So this is how you can solve this exercise, and there are some more parts not similar to this, but you can show that the energy, for example, F is actually to show that the energy of xt and its Hilbert transform are same. I will not give a hint to this. This is actually easier, so you should be able to do this yourself without any hint. So we will see you again in the next class.